Okay, so let's keep going. And so this is now section 10.3 on applications and higher derivatives. Up until now, we've done first derivatives. Of course, we haven't called them first derivatives because there's no need to use the term first until there's been a second and third and so on, much like the Great War wasn't called the First World War until after there was a Second World War. But we're going to start with the second derivative. So what is the second derivative? Well, very simply, second derivative is the derivative of the first derivative. So you have a function f of x, you take its derivative f prime of x, and then you go ahead and you take its derivative f double prime of x. In the language of and the other notation, if you have y, its derivative is the derivative of y with respect to x. And this one's a little kind of strange. It's the derivative of y with respect to x with itself respect to x. So you kind of see, and this is just notation, there's two d's, so d squared y, and on the bottom is a dx and a dx. So it's dx, and it should be in parentheses squared, but the notation that we use is just d squared y over dx squared. That's just our shorthand notation for the second derivative of y with respect to x. Now, what exactly does a second derivative give us? We know that a first derivative gives us a slope of a tangent line. So if you have a function like y equals, e to the x, maybe it looks like this. Then if I give you a random point, that's the slope of the tangent line, which means if I want to calculate the slope of the tangent line, I take the first derivative and plug in the value of x. We've done this before. What about the second derivative? Well, just like the first derivative gives you the rate of change of the function, right? F prime of x equals the instantaneous rate of change of the function f, or f of x. F double prime of x gives you the instantaneous rate of change of f prime of x. Each derivative gives you the rate of change of the previous derivative. So if you take a look at this picture here, notice how if I go slightly to the right, the derivative gets a little steeper. So not only is the function increasing, the function's on the way up, but the derivative is also on the way up because the derivative is getting bigger. So in this case, my function is greater than 0. I'm above the x-axis. The derivative is greater than 0. My function's increasing. But because the rate of change of the function's increasing, the second derivative is also greater than 0. The second derivative gives you the rate of change of the first derivative. If I have a function that looks like this, and I look at this point right here, for example, let's do the same thing. The function is greater than 0 because I'm above the x-axis. The derivative is greater than 0 because the slope of the tangent line is positive. But as I move down the line, the slope actually gets shallower. The slope goes down. Because the slope goes down, that means the derivative value is going lower, getting smaller. So the second derivative, the rate of change of the first derivative here, is actually negative. So in general, if a function looks kind of like a bowl, then the second derivative is positive. And if the function looks kind of like a hill, then the second derivative is negative. Why? Because the slopes keep getting smaller here versus here where the slopes keep getting bigger. A function might look like a bowl at one point and a hill somewhere else. In this area to the left, the second derivative is positive. In this area to the right, the second derivative is negative. And somewhere in between, there might be a point where the second derivative is equal to 0. What do we call a point like that? Where the second derivative changes sign. So definition, a point at which the second derivative changes sign is called a point of inflection. And in English, American English, we've always spelled inflection that way, but the book, so this might be a European spelling, spells it like that. It could be a typo, or it could be a different spelling. There's quite a few words that are spelled differently in one language versus the other. So we also, just to throw another definition, the concavity of a function is determined by the second derivative. If f double prime is positive, the function, at least at that location, is concave up. Because remember, it looks like a bowl. Second derivative positive looks like a bowl, so it's concave up. And if f double prime is less than 0, the function is, at least at that location, concave down. So second derivative positive looks like a bowl, concave up. Second derivative negative looks like a hill, concave down. And a point where the second derivative is 0 may or may not be a point of inflection. Remember, it's not defined in terms of its value. It's defined in terms of the second derivative changing sign. So if on the one side of the point, the second derivative is negative, and on the other side of the point, the second derivative is positive, we would call it a point of inflection. Second derivative being 0 may or may not occur. So here's an example. We have the function f of x is equal to x to the 4th minus 3x squared plus 2. And part A, it says, find the local maximum and minimum points justifying the nature of each. Now, this is an old question, which we know how to solve. And we're actually going to do it using the old technique and the new technique. In other words, yes, we have a way of solving it from before, but watch us now use second derivatives to accomplish the same goal. So if you want to find the local max and mins, we take the derivative. F prime of x is 4x cubed minus 6x. And we set it equal to 0. So we set it equal to 0. And then we figure out what values of x make this true. Well, if I factor 2x, I get 2x squared minus 3 is equal to 0, which means we have either x is equal to 0 or x squared is equal to 3/2, which implies x equals plus or minus the square root of 3/2. So the first derivative, the first derivative test, we would plug in those values. Now, square root of 3 over 2 is equal to approximately 1.22. Negative square root of 3 over 2 is approximately negative 1.22, and 0. Those are the 3 points. So what was the first derivative test? The first derivative test said, okay, we know the first derivative is 0 at these 3 locations. Are they maxes? Are they mins? Are they neithers? we got to take points in between, plug it into the first derivative to see whether or not the derivative is positive or negative, to see if it's going up then down, if it's going down then up, if it's going up, up, or down, down. So let's take a look. Let's start with the number 1, which is in this section here, right? Let's start with that one, just because 1 is convenient. If I plug 1 into the first derivative, 4 minus 6 is -2, I get a negative number, which means my function is on the way down in that whole region. On the other side, if I plug in -1, I get -4 plus 6, that's +2. My function's on the way up, which means we have a maximum at 0, up and down. If I go past 1.22 to like a gazillion, just a huge number, x cubed will dominate x, which means it's going to be positive. Or if you want to use a specific number, you can plug in 2. 2 cubed is 8 times 4 is 32, minus 12 is positive. And on the other side, if you plug in -2, you get a negative, which means we have a minimum, maximum, minimum. So that's the first derivative test. How would I use the second derivative test? Well, with the second derivative test, I'm going to go ahead and take the second derivative. Seems pretty appropriate. We have 4x cubed minus 6x is the first derivative, so that means 8x squared minus 6 is the second derivative. And I'm not going to set it equal to 0. I don't care where the points of inflection are. That's not my goal here. My goal here is to determine whether the points where the first derivative is 0, which are -1.22, 0, and 1.22, whether those points are maxes or mins. I don't care about the second derivative being 0. I care about where the first derivative is 0. What I'm going to do is I'm going to plug in those 3 points into the second derivative. Because what will the second derivative tell me? Whether it's concave up or down, whether it looks like a bowl or looks like a hill. If the second derivative is positive and it looks like a bowl, I must be at a minimum. If the second derivative is negative and I look like a hill, I must be a maximum. So if I plug in 0 into the second derivative, f double prime of 0, that is negative, which means 0 is a max, or technically the function at 0 is a max, a little shorthand here. And if I plug in 1.22 or -1.22, I get the square root of 3/2 squared is 3/2 times 8 is 12. 12 minus 6 is positive, which means plus or minus the square root of 3/2 are mins. So the second derivative test works better than the first derivative test, unless the second derivative is 0. If you calculate the second derivative, you get 0. It doesn't mean it's neither. It means the second derivative test failed. If the second derivative test gives you 0, then you have to go back and use the first derivative test. Or graph it, of course. There's, you can always graph it and see if it's a maximum or a minimum. You can use your calculator. But at the end of the day, the second derivative test does not work when the second derivative is 0. Now, there is a part B of this question. I kind of labeled this A and B, but it should be method 1 and method 2, using first derivative test or second derivative test. Part B says, find the interval in which the curve is concave down. We want to know where concave down, which implies, what does that mean? Where the second derivative is negative. Well, if I want where the second derivative is negative, I will do something similar to the first derivative test. I'm first going to set the second derivative equal to 0. So I get x squared is equal to 3/4. So x is equal to plus or minus the square root of 3 quantity over 2. Then I will make a number line. And plug in those numbers, square root of 3/2 and negative square root of 3/2. And then I'll plug in a number in each part to see where the second derivative is negative. If I plug in something bigger than the square root of 3/2, like 100, then it's positive, which means I'm concave up. If I plug in 0, it's negative, I'm concave down. And if I plug in negative 100, it's positive again, I'm concave up. So the answer here is from negative square root of 3 over 2 to positive square root of 3 over 2, where the function is concave down. Hopefully that makes sense. Let's do another example. Y equals 2x cubed minus 9x squared plus 12x plus 5. Question A, find the derivative of y with respect to x. Find dy over dx. No problem there. None of these are relatively straightforward functions. So we get 6x squared minus 18x plus 12. Okay, done. B, find the coordinates of the point in the curve at which the derivative is equal to 0. Okay, so set it equal to 0. 6x squared minus 18x plus 12 is equal to 0. All three numbers are divisible by 6, so let's simplify by dividing both sides by 6 equals 0. This looks factorable. X minus 2, x minus 1 is equal to 0. And therefore, we get x equals 1 and x equals 2. Okay, we love problems where the answers are nice and straightforward. So maybe 1 and 2, maybe the function has a max, maybe it's a min, maybe it's neither. I don't know. Let's keep going. Part C. Find the second derivative of y with respect to x. Okay, well, we have the first derivative, so just take the derivative of the derivative. We get 12x minus 18. And D, hence. What does hence mean? As a result of what we just got, determine whether the points are local max or mins. So I'm going to evaluate the second derivative when x is equal to 1, and this gives me negative 6, which is negative. And I'm going to evaluate the second derivative when x is equal to 2. This gives me positive 6, which is positive. So anywhere the first derivative is 0, like 1 or 2, and the second derivative is negative, that's a maximum because I'm concave down. And if the second derivative is positive, that's a minimum, I'm concave up. E, find the coordinates of the, and by the way, just going back here to part B, I didn't actually answer it. It said find the coordinates of the points on the curve. We just got the x values, right? So we have 1 comma something and 2 comma something, but we haven't yet gotten the y values. How do I know the y values? Second derivative gives me concavity. First derivative gives me increase or decrease, rates of change. Original function gives me y values. So if I plug 1 into the original, 2 minus 9 is negative 7. Negative 7 plus 12 is 5. 5 plus 5, I get 1 comma 10. And if I plug in 2 in, 2 cubed is 8 times 2 is 16. 16, 2 squared 4 times 9, 36. That's negative 20. Negative 20 plus 24 is 4. 4 plus 5 is 9. So I should get 110 and 2, 9. So E. Now it says find the coordinates of the point of inflection on the curve. Well, I see the second derivative is negative at one point and positive is somewhere else, so it does change sign somewhere. So where does it change sign? Well, set the second derivative equal to 0. 12x minus 18 is equal to 0. Gives us x is equal to 3 over 2. And if I do a number line, just to confirm that it changes sign at that location, I mean, it's obvious, but for rigorous sake, if I take something like 0, I get negative, it's concave down. 2, it's positive, it's concave up. So it does in fact change sign. What's the coordinates? Well, the x value is 3 over 2, but now I need the y value. And I'm lazy with something like 3 over 2. So 2 times 1.5 to the third power minus 9 times 1.5 squared plus 12 times 1.5 plus 5. And this gives me 9.5, which in fraction form, because I love fractions, is 19 over 2. So I get 3 over 2 comma 19 over 2. And that is my point of inflection. And if you actually graph this curve, it's a cubic function. We know what cubic functions look like. They look something like this. So we do expect on the left to be a max, on the right to be a min, concave down, concave up, and then somewhere in between to be a point where the second derivative is 0. So everything is exactly as we expect. So let's now go ahead and let's do exercise 10J. Exercise 10J. So the first question says, find the second derivative for the following functions. Okay, so question 1, part A. It says y equals x sine of x, and it wants the second derivative. Okay, how about we start by taking the first derivative, and then when we get the first derivative, we'll take its derivative. Unfortunately, I don't know of any shortcut that can get us from the function to the second derivative without passing through the first derivative. I would be interested in knowing whether such a thing exists, but in all my years, I've never even heard a hint of something like that. So the derivative of y with respect to x. So the first question we ask is, what rule do we use here? X sine of x, that's a product. X times sine of x. So we use a product rule. Derivative of the first, that's 1, times the second, which is sine of x, plus the first, which is x, times the second, which is cosine of x. So the first derivative becomes sine of x plus x cosine of x. And now we want the second derivative. Well, the second derivative is the derivative of the derivative. Here we have a plus sine of x plus x cosine of x. We know when there's a plus, you do each one separately. So the derivative of sine of x is immediately just cosine of x, plus, what's the derivative of x cosine of x? Well, what rule do I use there? That's a product. I will use the product rule, which says derivative of the first times the second untouched, plus the first times the derivative of the second, which is negative sine of x. So my answer is cosine of x plus another cosine of x for 2 cosine of x minus x sine of x. So that is A, green. Let's go to B, which says f of x is equal to 2 over the quantity x minus 3 squared. So there's 2 ways of doing this. One would be the chain rule. One would be chain and quotient rule. I think intuitively, even though it's not the way I would do it, I think our intuition would do it this way. So this is the way I will do it. But what I would do, just to let you know, is I would rewrite it as 2 times x minus 3 to the negative 2 power, and then use the chain rather than the quotient. But I'll use the quotient anyways. Derivative of the top, 2 is a constant. The derivative of the constant is always 0. So 0 times the bottom, which is x minus 3 squared. Quite often in math, what you'll see is something like 0 times a star. And basically a star is a placeholder for who cares? It's times 0 anyways, so why should I waste time writing it? So 0 times the bottom, whatever that is, minus the top times the derivative of the bottom. What's the derivative of x minus 3 quantity squared? It's a chain. The power comes down, drops by 1 when we leave the inside alone, multiplied by the derivative of the inside, which in this case is 1, over the bottom, which is x minus 3 squared. So what do we get? 0 times whatever is 0 minus, so I have negative 4 times x minus 3 over x minus 3 to the 4th, or negative 4 over x minus 3 cubed. 1 from the top cancels with 1 from the bottom. I'm going to rewrite this as negative 4 x minus 3 to the negative 3. And then for the second derivative, I'll do it the other way. I'll do it the way I would have done it, which is the power comes down and multiplies by the constant already there, which is 12, times x minus 3, power drops by 1 to negative 4, times the derivative of the inside, which is 1. And I just get 12 over x minus 3 to the 4th power. A little faster than the quotient rule, but I wanted to illustrate both ways. Okay, that's the second derivative, and now we go part C. It says s is equal to 2t natural log t. So when you have words, letters, whether cosine or sine or natural log, and especially when you have an s, which can often look like a 5, you want to be very careful how you write 2t ln of t. I'll put a little dot in there to make sure that you know it's not a 1 or any confusion at all. So s equals 2t ln of t. So we want the derivative of s with respect to t. This is a product of 2t and ln of t. Derivative of the first is 2 times the second untouched plus the first untouched times the derivative of ln of t, which is 1 over t, which simplifies to become 2 ln of t plus 2, because these t's, one on top, one on bottom, cancels. So what is the second derivative of s with respect to t? Well, it's going to be 2 ln of t. So the derivative of ln of t is 1 over t. So 2 times 1 over t, or just 2 over t. And then plus 2, the derivative of 2 is 0. So we just get 2 over t as our answer. And we're done. Second derivative. That's all I wanted. Yummy. Okay, so let's go ahead now and go to question number 2. It says let y equal x to the 5 minus 3x squared plus 5. And it says for part A, find any local maximum or minimum points in the curve, justifying whether they are maxima or minima. It just says justify. It doesn't say how to justify. So we can use the first derivative test, we can use the second derivative test, and presumably, if this is a test where you can use your calculator, then you can graph it, make a picture in your graph, and say, hey, look, get the max, it's min. Although I'm pretty sure they want it algebraically. Let's see how easy that would be. Y prime, the first derivative, is 5x to the 4th minus 3x, sorry, minus 6x, 5x to the 4th minus 6x. And we want to know when the first derivative is 0. So set it equal to 0, factor out an x, we get 5x cubed minus 6 equals 0. So we get x is equal to 0, or x cubed equals 6 over 5, so that x equals the cube root of 6 over 5. Are those first derivatives are those maxes or mins or neither? Well, let's do the second derivative test. Y double prime is 20x cubed minus 6. So what is the second derivative at 0? It is negative 6, which is negative. Negative means concave down. We got a maximum. And what is the second derivative at the cube root of 6 over 5? Well, if you plug in the cube root of 6 over 5 and you cube it, you get 6 over 5 times 20 becomes 24. 24 minus 6 is 18. 18 is certainly positive. That's a concave up, which tells me that we're dealing with a min. Of course, they did want the points on the curve. So 0 comma what? 0 comma 5 is my maximum. And the other one is, this is not going to be nice anyway, so I might as well use a calculator. 1.2 to the 1/3 power, the cube root of 1.2. I get an x value of approximately 1.06. And then if I do answer to the 5th power, minus 3 times answer squared plus 5, it gives me a y value of about 2.97. So I get 1.06, 2.97. And I justified max min. B, find a point of inflection on the curve. I want any point where the second derivative is 0. Okay, well, the second derivative is 20x cubed minus 6, set it equal to 0. So I get 20x cubed is equal to 6. X cubed is equal to 6 over 20, which is 3 over 10. So x is equal to the cube root of 3 over 10. And what is the cube root of 3 over 10? It is approximately 0.669. and that is between 0 and 1.06, concave down on one side, concave up on the other side. So our point of inflection is 0.669 comma, and then I just got to scroll up to my answer to the fifth minus 3 times answer squared plus 5, and that gives me 3.79. Nice calculator. It really simplifies my work. C. Hence, give the range of values of x for which the curve is concave up. Well, if I make my number line, I know that my point of inflection is here at 0.669. I know to the left of that, where am I? To the left of that, like it's 0, it's concave down. To the right of that, it's concave up. That's the only point of inflection, which means the second derivative never changes other than that one point. And therefore, the range of values for which it's concave up would be 0.669 all the way to infinity. Okay. Moving on to question number 3. It says, let y equal e to the x over x, and it says where x is not 0. It doesn't have to say that. It's obvious x can't be 0. I don't know why it says that. It does it often in the book. Completely unnecessary, but true. I'm not arguing with it. So part A, it says find the derivative. Okay, no problem. The derivative. Well, this seems like a job for the quotient rule. Derivative of the top, derivative of e to the x is just e to the x times the bottom untouched minus the top untouched times the derivative of the bottom, which is 1 over the bottom squared. So I get x e to the x minus e to the x all over x squared, which I can write because you have a single term in the denominator, so I can split it into 2 terms. So I can write it as e to the x over x minus e to the x over x squared. What's wrong with the previous way? Nothing, but I think this one makes the second part, which is finding the second derivative, a little easier. Why? Because we have the derivative of e to the x over x minus e to the x over x squared. Well, we've already found the derivative of e to the x over x. That was what we did in the first part, right here. We already have it. So I can just write it again. This is the derivative of e to the x over x minus, and now we want the derivative of e to the x over x squared. Well, that's another quotient rule. Derivative of the top times the bottom untouched minus the top times the derivative of the bottom over the bottom squared, x squared squared x to the 4th. So I get e to the x over x minus e to the x over x squared. I'll split up the next one as well. So minus e to the x over x squared minus the negative is plus 2 e to the x over x cubed for a final answer of e to the x over x minus 2 e to the x over x squared plus 2 e to the x over x cubed. So that's part A. Part B, hence, that means as a result of what we just found, show that there's a minimum point at x equals 1. Well, if I plug in 1 in the first derivative, I better get 0. E to the 1 over 1 minus e to the 1 over 1 squared, I do in fact get 0. How do I know that it's a minimum? Well, if I plug it into the second derivative, I better get a positive number so that it's concave up and it's a minimum. E to the 1 over 1 minus 2 e to the 1 over 1 plus 2 e to the 1 over 1 gives me e, which is positive. So it is concave up, and therefore it is a minimum. I don't know why I wrote those arrows. I never do that. Just the shape looks like that. It's a minimum. C, prove that there are no points of inflection on the curve. Prove that there are no points of inflection on the curve. That means there have to be no points where the second derivative is 0. Well, let's go back to the second derivative, which is this. Set it equal to 0 and see if we get nonsense. So the first thing I'm going to do is get a common denominator of x cubed. So multiply the first one by x squared over x squared. That gives me x squared e to the x. The second one I multiply by x over x gets me 2x e to the x. The third one I already have over x cubed, so I don't have to do anything with that, equals 0. Multiply both sides by x cubed, so that goes away. Remember, x can't be 0. Every term has an e to the x. Factor it out, getting x squared minus 2x plus 2 equals to 0. Exponentials are never negative, so I don't have to worry about that, which means if a product of two things is 0 and one of them can never be 0, the other one must be 0. So x squared minus 2x plus 2 would have to be 0. Well, that's a quadratic. Not factorable, so x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Already I see there's no real number. There's no solution here because I have a negative in the radical. So there's no real x value for which this holds. You might say, well, there's complex x values. And it's true, there are imaginary numbers, but getting into calculus of imaginary and complex numbers is complex. It's much more challenging and a lot of fun, by the way. One of my favorite courses in college was complex analysis. Just an amazing course. Still remember my instructor, Eugene Barston, the UIC. He was just an amazing instructor. I think about him often, just as a teacher. He just walk into class and say, "Oh, we're doing this today," and then just teach. No lecture notes, just go. He was amazing. Yeah, anyways, so there's no real numbers, and that answers the question. All right, question number 4. We have f of x equals x over x minus 3, and they're so nice telling me x can't be 3. Thank you so much. I wouldn't have known otherwise. That was sarcasm, by the way. A. Show that f is decreasing for all x values in its domain. Show that f is decreasing, going on the way down for all x values in its domain. Well, if the function is decreasing for all x values in the domain, its derivative would be would be negative everywhere. Let's see if that's the case. What rule do I want to use here? Let's go ahead and use the quotient rule. Derivative of the top is 1 times the bottom untouched minus the top untouched times the derivative of the bottom, which is 1, over the bottom squared. X minus 3 minus x, that gives me negative 3 over x minus 3 squared. X can't be 3, but any other point, x minus 3 squared is a positive number, negative number on top, so this is always less than 0, which means the function's always decreasing. B, show that f has no points of inflection. Well, you only have a point of inflection if the second derivative changes sign. Let's see if that ever happens. First, I'm going to rewrite f prime of x as negative 3 times x minus 3 to the negative 2 power. So I can immediately get the second derivative as 6 times x minus 3 to the negative 3, or 6 over x minus 3 cubed. Now, x minus 3 cubed could be positive or negative. In fact, if x is greater than 3, then f double prime of x would be positive. But if x is less than 3, then f double prime of x is negative. And it seems like it would change sign at 3. But it doesn't, because the function doesn't exist at x equals 3. There's a gap, there's a vertical asymptote. If you were to graph this function, hopefully you know how to graph it if you're in calculus, x over x minus 3. We first make a vertical asymptote at x equals 3, because we'd be dividing by 0. Non-zero over 0 is a vertical asymptote. There's no holes here. Nothing canceled to create a hole. We know that at x equals 0, the function has a value of 0, so the x-intercept, the only x-intercept, and the y-intercept is there. So now we want to graph. And we also have a horizontal asymptote at x equals 1, because the ratio of the leading coefficients is 1, x over x, same degree, 1 over 1. This one has to be here, because if it was down, there would be an x-intercept, and we know there's none over there. And similarly, this one has to look something like this because there is an x-intercept. So notice two things. On the left, it's more like a hill, concave down. On the right, more like a bowl, concave up. Certainly decreasing here, certainly decreasing there. So the function's always decreasing. It's concave down on one side and concave up on the other. But there is no point on the graph where it changes concavity. Nothing exists at x equals 3. So even though it changes sign, there's no point where it changes sign. Fun question. Questions like that are great because they're not just plug and chug and get the answer and just show that the formulas work, but they enhance our understanding of what's going on. Question 5. It says for each function below, find any local max and min, find the second derivative, find points of inflection, and find where the function is concave up and where it's concave down. So let's start with 5a. We have y equals x minus 2 cubed times x plus 1. Hopefully these functions aren't too annoying. So find any local max or min points. How do we do that? We take the derivative. This is a product rule. It's x minus 2 cubed times x plus 1. When we do the derivative of the first part, the derivative of x minus 2 cubed, and we ask ourselves, what do we use? What method do we use to take its derivative? We see that's the chain rule. It's something to a power. It's a function x minus 2 to a power. So it's 3x minus 2 squared times the derivative of the inside, which is 1, times the second untouched, plus the first untouched times the derivative of the second. So this gives me 3x minus 2 squared x plus 1 plus x minus 2 cubed. If I want to set this equal to 0, the first thing I'm going to do is I'm going to factor. Both terms have an x minus 2 squared. First term, I have a 3 times an x plus 1 remaining. Second term, I have an x minus 2 remaining. So this becomes x minus 2 squared. And then I'm going to multiply this out. 3x plus x is 4x. 3 minus 2 plus 1. So I have x minus 2 squared times 4x plus 1. Set it equal to 0 to solve. And I get x is equal to negative 1/4 and x is equal to 2. So I have two locations that might be a max and might be a min. Let's take the second derivative and go back to, this one here is probably the best form to take the second derivative from. It's certainly very simple. So the derivative of the first, 2x minus 2 to the 1 times the derivative of the inside times the second untouched minus the first untouched times the derivative of the second. This gives us 2x minus 2, 4x plus 1 minus 4 quantity x minus 2 squared. You could simplify this, and I personally would simplify it. And you know what? I'm going to do it anyways because I'm going to need it for the next part. But what I was going to say is that if all you're doing is plugging in values from part A, from negative 1/4 and 2, then you don't really need to simplify because you just plug it in and get a value. But since we're going to be using this to get the points of inflection, it'll help if it's simplified. So I'm going to pull out the x minus 2 that they both have in common. I'm left with 2 times 4x plus 1 minus 4 times another x minus 2 that I didn't pull out. So I have x minus 2 times 8x minus 4x is 4x, and then 2 plus 8 is plus 10. And I can factor a 2 out of that. So 2x minus 2, and then 2x plus 5. So that means if I want to know maxes and mins, I will evaluate the second derivative at negative 1/4. I don't care about its value. I just care about its sign. 2 is positive. Negative 1/4 minus 2 is negative. And 2 times negative 1/4 is negative 1/2 plus 5 is positive. I get 1 negative, so this is negative. And if I plug in 2, I plug in 2, I get 0. that tells me that the second derivative test does not work for that one anyway. If the second derivative test fails, I need to use the first derivative test. And of course, I don't really care about what happens on either side of 2. So I will plug in back in the first derivative. I will plug in 1.9 just to the left of 2. And I see if I plug in 1.9 and get positive, it's on the way up. And if I plug in 2.1, it's also positive on the way up. So 2 is neither. It's neither a max nor a min. But because the second derivative is negative at negative 1/4, then we have a maximum at negative 1/4, comma, and it wants the point. So to get the point, I got to go back to the original. And I have negative 1/4 minus 2 to the third power times parentheses negative 1/4 plus 1. And that gives me about negative 8.54. So there's one maximum at negative 1/4, negative 8.54. And the other one is neither. Our first neither, yay. Now they want any points of inflection. Well, to find points of inflection, I will make a second derivative number line. Whoops, a second derivative number line. And I'll put all the points where the second derivative is 0, which occurs at 2, and at negative 5/2. And then I will take a point in each section to see if the second derivative changes sign. If I plug in 3, I get a positive number in the second derivative, which means it's concave up. If I plug in, let's say 0, I get a negative, which means it's concave down. And if I plug in negative 3, I get a positive, so it's concave up. Which means there are 2 points of inflection, negative 5/2 comma something, and 2 comma something. What are those somethings? Well, we got to go back to the function. Well, 2 is easy, 2 comma 0, and negative 5/2. So negative 5/2 minus 2 to the third power times parentheses negative 5/2 plus 1. And this gives me about 137. Now, that's a big number. Just for fun, I'm going to graph this. Y equals x minus 2 to the third power times x plus 1. I'm going to graph it. If I'm really at negative 137, I better set my window. X min, let's say negative 3. So I can cover negative 5/2. X max, let's say 3. Y min, everything seems positive. So let's say negative 1, and Y max 150. And yeah, when I graph it, I do certainly see on the left side, it gets really, really, really up there. Negative 150, negative 137 seems very reasonable. And I am confident with my answer. Okay, so now we go to 5B. Oh, I'm not done yet. Sorry, not done yet. One more thing for this past one. It said, not only find the point of inflection, which we just did, but determine the intervals where the function is concave up and where it is concave down. So where is it concave up? Negative infinity to negative 5/2, and also 2 to infinity. And where is it concave down? From negative 5/2 to 2. And notice that second derivative number line answered both parts C and D. So dual purpose. All right, question B. It says h of x is equal to e to the negative x cosine of x, but we only care about 0 to 2 pi, a very small domain in the grand scheme of things. Okay, so first find any local mins or maxes. So first derivative, this is a product, e to the negative x times the cosine of x, e to the negative x. That's not e to the x, it's e to the negative x, which is a function of a function, which means it's a chain rule. And we get the derivative of the outside is e to the whatever times the derivative of the inside, which is -1, e to the negative x, the derivative of negative x is -1, times the second untouched, plus the first times the derivative of the second. This gives us negative e to the negative x cosine of x minus e to the negative x sine of x, which I can factor out to e to the negative x, and I'm left with cosine of x plus sine of x. And we want to know where the first derivative is 0. Well, exponentials are never 0. So if I want to set this equal to 0, it's so h prime of x is equal to 0 if and only if cosine of x plus sine of x is equal to 0. And this is true if sine of x is equal to negative cosine of x, which is true when tangent of x is equal to -1. And I did that by dividing by cosine of x on both sides. Of course, you have to be careful there if you're going to divide by cosine of x, because you don't want to divide by 0. But if cosine of x is 0, sine of x can't be 0. So there's no solution when cosine of x and sine of x are both 0. I don't have to worry about it. And then if I draw my unit circle, where is tangent of x equal to -1? Hopefully you know this. It's here and here. And I only care about 0 to 2 pi. So I get x is equal to 3 pi over 4 and 7 pi over 4. Those are the only x values where tangent of x is -1 between 0 and 2 pi. Okay. So what do I do now? Well, are they maxes or are they mins? So let's find h double prime of x. We're going to need it anyways. So if I go back to up here for h double prime of x, it's a product, negative e to the negative x times cosine of x plus sine of x. So the derivative of the first is negative e to the negative x times -1 times the second, which is cosine of x plus sine of x, plus the first, which is negative e to the negative x, times the derivative of the second, which is negative sine of x plus cosine of x. So this gives us e to the negative x cosine of x plus e to the negative x sine of x plus another e to the negative x sine of x minus e to the negative x cosine of x. So this gives me 2 e to the negative x sine of x as the second derivative. Wouldn't expect that, but it is what it is. Okay, so now we're going to plug in each of the original 2 points into this to see if it's positive or negative. What's the second derivative at 3 pi over 4? Well, 3 pi over 4 is in the second quadrant, so sign is positive. Exponentials are always positive. So this is greater than 0, which means it is a minimum. And if I do h double prime of 7 pi over 4, that's in the fourth quadrant. That's negative, so it's less than 0. So that's a maximum. So we have a min at 3 pi over 4 comma something and a max at 7 pi over 4 comma something. What are those somethings? Well, we got to plug it into the original problem. So 3 pi over 4 is about 2.35, 2.36. So e to the power of negative that number times cosine of that number gives us 0.0947. And if I plug in 7 pi over 4, and I do e to the negative of that number times cosine of that number, this gives us 0.00408. So those are my mins and maxes. We also already found an expression for the second derivative. Now we want points of inflection. Points of inflection are where the second derivative changes sign. So let's set the second derivative, which is 2e to the negative x sine of x equal to 0. This is never 0, so I don't have to worry about that. When is sine of x equal to 0 from 0 to 2 pi, x equals 0, pi, or 2 pi. Of course, this is not a full number line. This is a 0 to 2 pi line segment. So I don't have to look on the other side of 0 and 2 pi, so they're not points of inflection because nothing changes sign on the edges. And if I want to evaluate before pi, sine of x is of course going to be positive, so it's concave up, and after pi it's negative, so it's concave down, which means point of inflection would be pi, comma, whatever its y value is, which is e to the negative pi times cosine of pi. Cosine of pi, of course, is negative 1. So this gives me 0.043. Oh my God. Oh no, no, no. I'm in degree mode the entire time. Oh, I just saw that. Wow. Oh, horrible. Did I make any earlier mistakes? No, this is the first trig problem. Wow. Let's go back here and fix these values. Oh my God, I just noticed. Classic rookie mistake. Oh, wow. Good thing I noticed that. I only noticed because I noticed that cosine of pi has to be a negative number, and I didn't get one. Oh my God. So let's just do e to the pi cosine of pi again. Now it's negative, negative 0.043. Wow, what a mistake that was. And just to go back for completeness sake to 3 pi over 4, back in the original function, e to the negative 3 pi over 3 pi over 4 times cosine of 3 pi over 4. That would be negative 0.067, and e to the negative 7 pi over 4 cosine of 7 pi over 4 gives us 0.0029. And I know that's not the right number of significant figures, but I kind of ran out of room. Sue me. Okay. And of course, we want the intervals of concave up and concave down. So it's up from 0 to pi, and it's down from pi to 2 pi. Okay. And then we go to question C. So here we have f of x is equal to x cubed e to the negative 2x. So first thing we do, f prime of x, derivative of the first, 3x squared times the second, plus the first untouched, times the derivative of the second, e to the negative 2x times negative 2. If I factor out an x squared e to the negative 2x, I'm left with 3 minus 2x. Where is this equal to 0? When x is equal to 0 or x is equal to 3 over 2, because exponentials are never 0. I want the second derivative now. So go back to this stage here. It's a little easier to do it from there. I get the derivative of the first 6x e to the negative 2x plus 3x squared e to the negative 2x times negative 2 minus 6x squared e to the negative 2x minus 2x cubed e to the negative 2x times negative 2. Simplify, this becomes 6x e to the negative 2x minus 6x squared e to the negative 2x minus another 6x squared e to the negative 2x plus 4x cubed e to the negative 2x. This gives me, after factoring out, well, let's do one step at a time, 6x e to the negative 2x minus 12x squared e to the negative 2x plus 4x cubed e to the negative 2x. I can then write this as 2x e to the negative 2x times 3 minus 6x plus 2x squared. So f double prime of 0 is 0, inconclusive. F double prime of 3 over 2, positive 3 minus 9, I'll do my calculator. 3 minus 9 plus 2 times 1.5 squared. This is negative, which means that is a concave down, therefore that is a max. But what about 0? I'll make a number line for f double prime, or for f prime. This is an f prime number line. And the question is, what does it look like to the left? What does it look like to the right? So if I plug in just a number slightly to the left of 0, like negative 0.1, I get a positive, it's on the way up. And if I do positive 0.1, it's also positive, which means 0 is neither. In terms of an f double prime number line, an f double prime number line, we know that x equals 0 is already going to be on it from this part right there. And we also have to solve 2x squared minus 6x plus 3 is equal to 0. So x equals negative b plus or minus the square root of b squared minus 4 times 2, 8 times 3 minus 24 all over 4. So that's 6 plus or minus square root of 12, which is 2 root 3 over 4. So that's 3 plus or minus root 3 over 2. 3 plus the square root of 3 all over 2. That's 2.37. And 3 minus the square root of 3 all over 2. That's 0.634. So we have to add those 0.634 and 2.37. And then we want to check second derivative. So if I take a number like 100, that's certainly going to be positive. If I take 1, 3 minus negative 3, that's negative. And if I take a number in between there, it's also positive. And if I go to like negative 1, I get negative as well. So the points of inflection are going to be 0 comma something, where it changes sign. 0.634 comma something, where it changes sign. And 2.37 something, where it changes sign. What are the y values? If you go back to the original function, 0 will of course give me 0. 0.634 to the third power times e to the negative 2 times that number. This gives me 0.0717.
There.
And the other one, if I plug in 2.37, I get 2.37 to the third power times e to the negative 2 times 2.37, and that gives me 0.117. And therefore, I want the intervals where it's concave up. The intervals where it's concave up would be 0 to 0.634 and 2.37 to infinity. And where is it concave down would be negative infinity to 0 and 0.634 to 2.37. So that takes care of question number 5. And question number 6. It says a population P at a given time is given by the following equation. P of T equals 10 over 1 plus 4e to the negative 2t. This is called a logistic equation. It's a very, very famous type of equation, which you'll see when you get to differential equations. So part A, it says find an expression for P prime. Derivative of the top is 0 times the bottom, who cares, minus the top times the derivative of the bottom, which is 0 plus 4e to the negative 2t times negative 2 all over the bottom squared, 1 plus 4e to the negative 2t squared. This gives me 0 times whatever is 0, minus 10, negative 8 plus 80. So I'll just do 80 e to the negative 2t over 1 plus 4 e to the negative 2t squared. Then it says, explain why p prime is greater than 0 for all t greater than or equal to 0, because everything is positive. Interpret your result in the context of population growth. Populations, if you just have a population with no predators, with nothing around to destroy the population, predator-prey models are a very important branch of differential equations. Then you expect the population to increase. So population growth is going to be positive. B, find an expression for p double prime of t. Great. So the derivative at the top is 80 e to the negative 2t times negative 2 times the bottom, which is 1 plus 4 e to the negative 2t squared. This is p double prime. Minus the top, 80 e to the negative 2t times the bottom, which is 2, 1 plus 4 e to the negative 2t to the 1, times the derivative of 1 plus 4 e to the negative 2t, which is 4 e to the negative 2t times negative 2. All over the bottom squared, which is 1 plus 4 e to the negative 2t squared squared to the fourth. So we get negative 160 e to the negative 2t times 1 plus 4 e to the negative 2t squared plus 1280 e to the negative 2t, 1 plus 4 e to the negative 2t. That should actually be e to the negative 4t. I'm working quick because I'm running out of time. I'm hoping this is correct. All over 1 plus 4 e to the negative 2t to the fourth. Cancel 1, cancel 1, cancel 1. And we get negative 160 e to the negative 2t minus 640 e to the negative 4t plus 1280 e to the negative 4t all over 1 plus 4 e to the negative 2t cubed. So we get negative 160 e to the negative 2t plus 640 e to the negative 4t all over 1 plus 4 e to the negative 2t cubed. Find when the second derivative is equal to 0. Well, the second derivative will be 0. A fraction is equal to 0 when the numerator is 0. So p double prime equals 0 implies 640 e to the negative 4t equals 160 e to the negative 2t. If I divide by 160 on both sides, I get 4 equals, if I multiply e to the 4t, e to the 2t. So the natural log of 4 equals 2t, and therefore t is equal to the natural log of 4 over 2. The natural log of 4 over 2 is approximately 0.693. Explain the significance of this point in the context of the rate of the population growth. So what's happening is it's growing fast, point of inflection, it slows down asymptotically. So this is a point at which the rate of growth slows. Part C, for the value of t found in part B, find its y value. So go back to the original function. 10 divided by parentheses 1 plus 4 times e to the negative 2 times answer. And we get 5. Wow. P of 0.693 is equal to 5. Coincidence? It's exactly half of 10, which was the numerator. Explain the significance of this point in the context. It's the halfway point between the asymptotic maximum and the start, which is when t is equal to 0, 2. So it actually doesn't start at the origin. It starts, because it started 0, would never grow. You have to have some to begin with. But 5, the halfway point for the maximum population, is where it stops growing and it starts shrinking. Woo, okay. So the numbers came out right at the end, so I assume everything was great. This is the first half of 10.3, and I will do the next half of 10.3 shortly. So I will see you there.